Today we'll discuss about some beginning of functional analysis. Okay, let's start. Okay, so my voice is clearly audible now? Okay, so functional analysis. Okay, so uh, it's a lot of application in the domain of partial differential equation as well as numerical analysis, and many more. Okay, so Uh, what is functional analysis? And before going to deep study in this course, we'll start with metric space. Okay, and so why we'll need metric space? Uh, we'll learn later. But first, we will start. What is metric space? Okay, so suppose suppose you are given some non-empty set. Okay, so if the set is empty, then what happened? Can you tell me? Hello? Hello? Am I audible? Okay. So if X is a empty set, then anything can be vacuously true. So we are omitting that case and we are only considering the case when X is a non-empty set. Okay. So suppose X is a non-empty set and D is some function that is a mapping from X cross X to the set of all real numbers. Okay, actually it is not all real number, it is the non-negative real number. Okay, so how it is defined? And this D, basically it is nothing but the uh, distance function, and it is called metric. And which condition it will satisfy? The first condition is D of xy, that is always greater equal to 0 for okay, and it is 0 if and only x equal to y. And suppose and what is the distance between d of xy? That is the same as the distance between y and x. Okay, and the last one is triangle inequality. If you are considering some other point that is distinct from x and y, in that case d of xy is always less or equal to d of xz plus d of zy. And this four, if D satisfy these four conditions, then it will called a metric. And now X with the along this metric D, it is called a metric space. Okay, so okay, ha 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 ha. No, I told you that for X is a non-empty set, I can define a mapping from D cross X to the set of all non-negative real numbers. It is not on x cross y. Okay. Clear? Basically, I am considering two elements x and y. That two elements are from x. And that's why. Okay? Clear? So, can you give me some example? Which example came to your mind? What is that? That is nothing but if you are considering the set of all real numbers, then okay. In that case, what is the distance between two arbitrary point in R? What is the distance? Hmm,
Modulus of x minus y.
okay, that get. Now, if we consider t of xy equal to this, whether this form a metric or not. So first, if you are considering two distinct element, so if we are considering two distinct point, so obviously their distance is always greater than zero, and it is zero if and only x and x equal to y, because this mod function is always get equal to zero, and it is zero if and only this x minus y equal to zero, and that implies x equal to y. So the first two conditions are satisfied. Now, what is our third condition? If you are considering d of x y x minus y, that is same as the modulus of y minus x. So the third condition is also hold true. Now, what about the fourth condition? If you are considering d of x y, that is x minus y, in that case, you can use the triangular inequality for modulus function. In that case, so condition 4 is also hold true also. So that's why it's from a metric. Is there any doubt?
No, sir.
Okay. No, proceed to these examples are you are considering in R. But if you are considering some uh, abstract space, you don't have any modulus function. In that case, can you define? Suppose X is just a non-empty set. You don't know anything about anything else about this set. Can you define some metric here?
Mm,
Indiscrete metric? Is there what is indiscrete matrix? That is discrete matrix. D of x y.
okay.
That is
Okay.
that is
Uh,
that is one
that
if
if we dxy
x
equals
is
to 1, if x not equals to y, and if 0, it's x equals to x, y.
okay, fine. So in that case, you can define some metric, and for any non-empty set, this metric will work. And the x with this d metric, this is called discrete metric. And this metric space has lots of nice properties, and so we'll discuss it about later. We'll see that in this space, lots of things behaves quite differently compared to the other spaces. Okay, now so suppose X is just a non-empty set. How how many possible how many metrics you can define in a non-empty set? Sure, you are only given that. You are only given, and just suppose X is a non-empty set. Okay. So how many metric you can define? It is only given. It is only given that X is a non-empty set. Nothing else. So how many possible metric you can define here?
I guess infinite, because if we change the function one to
Obviously, if D is a metric on X, in that case KD, it is also a metric on X, where K is a non-negative real number. That is fine. But is it always true? Suppose I am considering X with only single element. Then how many possible metrics you can define on X? There are only one metric, and that is d of a equal to 0. Nothing else. If X is contained at least two element, in that case, if D is a metric on X, then KD is also a metric on X where K is a greater than 0. So if the cardinality of X is 1, then only one metric you can define. But this is very tricky question. So it is obvious that if you can define one metric in on X, then you can define infinitely metric. But provide there is one exceptional case, that is if the cardinality of X is also, 1, and that means X is a singleton set. In that case, only one metric you can define. Okay, and suppose X is contain only two elements, then how many? What are the possible metrics you can define?
infinite.
First, what should be the metric? D of AB equal to 1. Okay. If this is a metric, in that case, there is KD. That also form a metric on X. So there are infinitely many possibilities on X. Okay. So the thing is clear. Okay. Okay. Now we'll proceed to some difficult, uh, not difficult, but a little bit of tough examples. Okay. So, do you know sequence space or L infinity space? L infinity space. What is that? Set of all bounded. So that means this is nothing but set of all bounded complex sequences. Okay. So how do you write it mathematically? Can you write it? So it is basically the collection of all such sequences such that mod of xm is less or equal to cx for all n belongs to 8 for some cx greater than 0. Is not it?
Hmm.
Is it correct? Is this correct? Okay. So in this space, I am defining some metric. So if each element of L infinity, that is a bounded sequence. So yeah, that means each sequence, each element of L infinity, that is one sequence. Okay. So how can you define some metric? Suppose you are considering two sequences x and y from L infinity. In that case, it has set up all bounded matrix. So, sup- okay. So whether this is your homework, and that is whether this D, that means the sup metric, whether it forms a metric or not. Okay, so I am as I am telling that is suprametric, so it obviously forms a metric, but check it yourself whether this will form a metric or not. Okay. So first thing is clearly the modulus function is always a non-negative function. That's why its supremum is also a non-negative. So condition one is done. And for condition two, if supremum is zero, in that case, each term will be zero because modulus function is always a non-negative term. And so in that case, xi equal to yi for all I, and in that case, the sequences become same, x equal to y, and same thing for the other side, opposite direction. So for one condition one and two holds true, and same as condition three. Now, if you are considering the third condition, in that case you have to for each xi minus yi, in that case for some different, this strictly follows from the triangle equation. Now which holds for all I belongs to n. So you can define supremum of xi minus yi. You are fixing the left hand side. It obviously less or equal to xi minus zi plus zi minus yi,
Hmm.
and it obviously less or equal to supremum of xi minus zi plus supremum of zi minus yi. So d of xy is less or equal to d of xz plus d of zy. So L infinity with this matrix D, it's form a matrix space. Is this clear?
Yes, sir.
Okay. Now this is your example three. Now you all know about LP space. What is LP space? Can you tell me
So,
what is LP space? What is LP space? Can you tell me? It is also a collection of all such sequences, but here where P is greater equal to 1, and here it is also the set of all sequences, so that it P is sum is not non-negative. The series of its Pth sum, that is the convergence series. Okay, so in that space we are defining some metric. Whenever you want to prove this, this is a metric space, you need lots of calculations using Minkowski inequality and Holder inequality, and lots of things are there. A little bit of lengthy proof, so I am omitting this proof. You can check it yourself. And oh, and one more thing, I am following the books of introductory functional analysis. Functional analysis. It is written by, okay, and this is very good book for the beginner of functional analysis. You can visit there, and the PDF file is also available in the internet, so you can access the soft copy also. Okay, so now there is another metric space. Mm, um, mm, C of AB. Any idea what is that? Okay, so that means this is set of all real valued continuous functions defined over. Okay, and here the metric is defined by, any idea how it is defined? There is maximum of, and you can define that metric also. That matrix, suppose this is your D1 and D2 FG. Mm, that is integration of A to B. Okay. And these two metric you can define on the space, and we'll see later some examples. And these two metric spaces are quite different. Okay, and okay, so and not only that, the open balls. Okay, so what is open ball and what is open set over? I will discuss it later. For today, um, C00. What is that? C00? Okay, so you, I will discuss it later. And that is, it is not a closed set of a closed subset of L infinity. Okay, for today. That's much for today. Okay. I hope you are enjoying this lecture.
Yes, sir.
Suppose you are. What is the distance between two sets?
Infimum of d of xy, as that x belongs to A and y belongs to B.
Okay, very good. So, if you are considering two disjoint closed set, in that case, the distance. What should be the
Maybe
distance?
zero, may not be zero.
Can you tell me the example? Uh, the distance may be zero.
E to the power x and x equals y equals to zero.
E to the power.
E to the power x and disjoint
Ah,
বলছে না e to the power x and y is equal to zero.
okay, very good. Very good. Very good. Okay. And some. Mm, okay, okay. Tomorrow we'll discuss lots of interesting examples. Okay.